Okay, now back to normal after we do read connection. Enter. Okay, yeah, sometime internet issues, you just retry. Click the retry button. Okay, seems like everything is okay. You can move this further down as well, or you can also enter this to make it readable. Actually, this rack, okay, register data type. Okay, and then once everything is okay, you save it. Okay, it will do the saving process, and then you close it. Okay, now back to our gedit, into our command line editor. Okay, and then what to do? Okay, make it bigger. Okay, you already finished this. Okay, to see what inside the folder, you can also type ls lah. Okay, ls. Now you have the multiplier.v. Okay, you have one file inside. Okay, then you need to write the test bench. So you repeat step number 8. Just repeat step number 8. Okay, this one. Right click and open a new terminal. Or in this case, we already in that terminal. Okay, you just type gedit multiplier underscore tb, same as this name. Okay, you type gedit multiplier underscore tb. So gedit means that we're creating another file. You can just type tab. You tap, hit the tab button, it will go to its previous memory and then underscore and then tb. And that's the fastest way lah. Okay, and then you enter. Now it will create you, give you the editor. And then what we do, okay, we select this code. Okay, make sure the code is correct lah, otherwise you will have problem. Okay, and then make it bigger to see it clearly. Okay, and then you do the editing lah. It's better for you to write this lah, okay, but to avoid error due to typos, then we copy and paste. Okay. So we have initial blocks with begin and end, and then we have end module. Okay. Double check. Okay, try to understand the code. Okay. So initial we have begin and end. So this actually to create a clock. Okay, to create a clock with 10 time unit lah. Okay. So inverted every 5 time unit. So it's actually 10 time unit clock period. So initial begin and then we reset it. Okay. And then okay, we start another loop. Finish and then end. Okay, so just check the loop now. So this begin and then the end or the closing loop, and this begin and the closing loop end. So this is for generating a clock. Okay, these two lines. Okay, and this one for reset. Okay, and this one, okay, for what we call as generating the input. So you can tap in to make it readable. Okay. Okay. Okay, so we have begin, but we didn't see any end yet. So this is actually the end. So for this one, I believe this begin and this is the end. Okay, I'm sorry. This begin, okay, and this is the end, the inner first. Okay, and this begin. So we can tap more to see it clearly. Okay, and then this end belong to this begin and display, and this end belong to this begin. Okay, you can readable like this one. Okay, you can even do like this one. So you can see the block. So this one block, second block, third block. Okay, and this is another block of begin initial. So you see the word monitor, okay, and display. This actually just to display the output, okay, during the simulation. So you can save it. Okay, just check whether your design is connected or not to the test bench. We didn't see it here. Okay, my design is not. Oh yeah, okay, here. This is very important. This is where you connect your design. Okay, multiplier is your design. Multiplier underscore TB is your test bench. Okay, this is your test bench. Inside your test bench, you instantiate your design. Okay, you give it any name actually. In this case, we give it as DUT, the name, and then you connect the clock of the design to the test bench. And connect the reset of the design to the test bench, and then you connect the in 0 to the test bench, and in 1 to the test bench, and out to the test bench. To see it clearly, maybe I can sketch something before we save it first. Then I sketch something. Okay, we can sketch it. Okay, right. So multiplier dot underscore TB multiplier underscore TB. So we have two files, multiplier TB and multiplier. So this is your design file, design file. Okay, design file. Sorry, let me admit better. I type. Okay, and this is your test bench. I just type easy. Your test bench file. Okay, and this is your design file. In this case, multiplier. In this case, so your design file name is multiplier.v, and your test bench file name is multiplier underscore tb.v. Okay, so just to recap, so this is actually for test bench. Okay, you need to have this file, and this is your design file. Okay, where this file will be used to generate the final chip. Okay, this is for the behavioral simulation to make sure the behavior of multiplier function as expected. So in terms of diagram, so we instantiate, we call the multiplier design inside the test bench. So remember, multiplier, this is the multiplier, and we have the how many input? 1, 2, 3, 4 input. Input clock, input reset, and input in 0 and input in 1. And then we have only one output. So this is 16-bit. Okay, and this is 1 bit. No need to label 1 bit. And then input, both input in 0 and in 1 is 8-bit. So both 8-bit. Okay, somewhere. Okay, maybe somewhere here. 8-bit. Okay. Okay, so we label the input here. This is CLK, CLK. Okay, and this one is RST, and this one is in 0. Okay, and this one is in 1. Okay, so this is out. Okay, so for the test bench, it's actually we have the same I/O. Okay, but the I/O is actually connected to the I/O of the test bench connected to the design. So this is your design with those input and output. Okay, 4 input and 1 output. This is 16 bit. This is 8. Both of these 8. So your test bench is actually, I just use different color. This is your test bench. It's connected to the design, and that's actually the purpose of instantiation. Okay, same. This is 16 bit. This is 1 bit, and this is 8 bit. Has to be the same. See, out is 16, in 0 and in 1 is 8 bit. So this is actually your test bench. You supply the stimulus, the input, and then you monitor the waveform at the output. So this is the output, and this is the input. So remember, in test bench there is no I/O port. Okay, just a register and wire, because you want to measure the output and also supply the input. So supply the input normally is registered at the time. Okay, how do we supply the input? Is basically we generate the input in the test bench. So this is how we generate the input. So the clock, we set it to 0. The reset it to 0. Initial value. Clock 0 means that your reset will start at 0, and same as your clock will start at 0, and then it turn up to 1. Okay, and then 0 again, and then 1. Why we get this pattern? Because we have the always block. So the always block will create the repetitive pattern like this one. So it repeat for every 10 time unit. Okay, every 10 time unit, which is, this is the T, the clock period, equal to 10. Why 10? Because this is 5. 5 for first value, which is here, and then another 5 is here. Okay, altogether 10. So it keep repeating, right? So that's for the clock. Okay, we supply here the clock CLK, same as reset. Okay, we reset initially 0, so we supply here. And then the reset actually after 10 time unit is become 1. So initially reset is 0. So 0 for how long? 5 time unit. Okay, and then reset equal to 1. For how long? 10 time unit. A bit longer. And then goes down, and then back to 0 for another 10 time unit. And then it continues 0. So this is the reset signal where we supply it in here. Okay, supply in here. Okay, reset. And in terms of input 0 and input 1, so this is the process. Okay, input 0, you look at here, input 0 become 1, and input 1 equal to I. So it means that input 0 always 1. Always 1. And input 1 depends on I. So I is actually will count up from 0 until 256. Okay, why 256? Because it is 8 bit. So the maximum of 8 bit is 256. Okay, so it will count up until 256. So I equal to input 1 equal to I. So input 1 equal to 0, 1, and so on. Okay, all right. So like this one. So input 1 is 8 bit, so it has 8 bit representation of it, whereby the first one is 0. Okay, second one is 1, and so on. So 0, 0, and 0, so on. Okay, so just a revision. Actually, you can check inside your previous year lecture lah, NT353 or digital IC design. So to start the simulation, we go back to our. It's always when computer in idle mode on the remote side, you need to retry to reconnect it. Okay. Sometimes you need to re-enter the password. Okay, and then unlock. And back to here. Then you save. And then you close it. And we back to the terminal. Okay. And then what you need to do is you need to source the software. Okay. You just type source, white space, and then / Synopsys. Okay. Type it clearly. So it's Synopsys. Okay. And then .sh and try to enter. Then when you get it okay, and then you will see it like this one. Okay. Some students they forgot to put the white space here. So when you forgot to put the white space, you enter and then it will tell you no such file in directory. Means that you need to have a white space actually. That's a command that you need to remember. So you just use the up and down arrow on your keyboard like this one. Okay. And then you recall your previously written command. Then enter. Now it's ready. And then we will start do the compilation to see the waveform. First, to see the waveform, we need to compile it first. Okay, you can skip this step. Okay, we go straight to the one with the waveform. So I think we have. I think this is already the step. Okay, we type VCS. Why VCS? Because we call the software package inside the Synopsys. So VCS white space minus R, then white space minus debug, okay, underscore all, okay, dash GUI, and multi, and I think just use the tab, no, this time, multiplier, okay, multiplier, sorry, multiplier, we already use the tab, I think, dot V, okay, multiplier, dot V, then white space and tab, okay, underscore T tab, okay, easy, okay. Tab is to use the previous, is to call the existing file inside the folder, the name of the file, okay. And then you enter. Once you enter, the compiler will do the compiling process lah. If no error, and then it will straight away bring you to the GUI, which is the simulator. If there is an error, it will not bring you to the GUI. You need to go back to the editor and then edit. So in this case, no error. You get this one, DVE, okay? The DVE command line also here, okay? Okay, and then what to do next? You click here, okay, to explore the waveform, okay? So before that, please note, if you encounter errors after executing the above command, please repeat the step 8. Okay, if no error, and then proceed to step 13 lah. If you have error, means that you have a syntax error. You need to go back to either multiplier.v or multiplier_.tb. So the command line will tell you lah, the terminal, okay, which file that has error. Okay, so you need to go back to that file using gedit command, okay, gedit multiplier.v for example, and then you check the coding in terms of syntax violation, same as multiplier_tb. If the command terminal mention the errors from the multiplier_tb, and then you need to type gedit from the command terminal multiplier.v, multiplier_tb.v, and then you check the syntax violation there is inside the file. Okay, it will also mention to you the line number where the errors actually happen. All right, back to our step number 13. So to explore the waveform from the variable window, okay, so I already snapshot here, okay, variable window, okay, to see it clearly, maybe we can check here. So this is the variable window. Okay, you click this, means that we want to include all the signal and the bus. Those with 1 bit we call signal, like this one, signal. Those with more than 1 bit we call bus. Okay, let's say we want to add all. We just press the shift button and then select all. Then you right click, okay, add to wave, and then new wave. And then you can see the wave. So the step is already mentioned here. Okay, add to wave, new wave. Okay, and then run DVE command. So before you run the DVE command, you need to know how to run it. So normally we type the run in the DVE command here. Okay, so this is the DVE command. So you can make it bigger. Okay, make this one bigger as well. Okay, and then you type RUN and then enter. And then you should be able to see this waveform. Okay, this is actually not a zoom in version. This is not a zoom in version. You click here to activate this part. Okay, and then you click this zoom full, and then you should be able to see all the waveform. Okay, to see it clearly, you just click again inside this to activate this part. Okay, okay, and then you click zoom 2 times, for example. Okay, and another zoom until you clearly see the waveform, like this one. Okay, now we can see it clearly, so move it. Okay, okay, here is the what we call as the output. So we have the input port, input 0, input 1. Remember, input 0 always 1 the value, because we set in our test bench. Where's the test bench? Okay, remember. So input 0 always 1. Remember this, I use different color. Okay, it's always 1. Okay, sorry. Okay, sorry. This is input 0. Always 1. Input 1 equal to I, whereby I is count up. Okay, counting up, because we mentioned here I equal to I plus 1, increment by 1 from 0 until 255, and that's why you can see here it's increment I1 from 0, 0, 0, 1, okay, 0, 1, 0. So this you can change the radix actually. Let's try. Okay, set the radix to unsigned decimal. Unsigned, this is hexadecimal right now. Unsigned decimal. Unsigned. No, binary. Set it to binary, sorry. Okay, now you can see in binary form. Okay, 0, 0, 0, 1, 1, 0, and so on. But this one, you can change actually to many type, different type of value Okay, all right. Okay. Now you can see clearly. Because it's 8-bit, we cannot see it so clear until we zoom it. Now 0, 0, 1, 0, 0, 1, 0, and so on. Okay, and then you can see the operation. So in here is the clock. You check the clock whether the clock is as expected or not. Okay, something wrong somewhere. Okay, okay. So how long is the clock? Is that correct? 10 time unit. Okay, and then you can check here. Okay, you can also analyze the output of the waveform. You can bring it here. Okay, you see the input 0 multiply with input 1. So input 0 always 1, right? Okay, 1 multiply with any value, you will get that value back. Okay, so to see it clearly, maybe you can change the value back to unsigned decimal. Here also unsigned decimal, and then you will see it. Okay, so what's to do? Let's say you want to see it in a meaningful manner. So maybe you can change the in 0 to become any other than one value, maybe 3 or 2, and then you can see, should be able to see the different output. Okay, you can also change this, depend on your programming skill. Okay, your HDL skill. So, but our intention is not actually to verify, to mark on this. Okay, we want to proceed to the next step. Okay, so we'll go back to the lab module. Okay, what's next? Okay, so we have this waveform, and then we zoom it already. Then we also change the radius. Okay, end of lab 0. Okay, now you can move on to lab number 1. Okay, so I stop this recording first, and then we shall continue to lab